Okay, good evening and welcome to week 5, day 1 of Delta Platoon. Today we're going to be talking about uh, data structures. Should be a little bit of a review of some of the concepts you've learned and used before. So who can give me some examples of data structures that are used in programming, some common ones?
Linked list.
Yep, linked list. So you've also got arrays, graphs, lists, trees, stacks, queues. Um, it's a pretty long list. And basically, I mean, you can think of data structures and algorithms are kind of the two core concepts that will help you to optimize your programs. So data structures, the goal today is to understand a couple of different data structures, those being stacks, queues, and linked lists, and how they organize and store data. Or like, so why? Because like I said, programming is about data structures and algorithms. So you got to have a means of storing data, and you have to have a means of solving problems using that data. And a data structure is just a means of organizing, working on, and retrieving data. Because like at its simplest form, like programming is take an input, you process the input, and you produce an output. And it's basically optimizing those three steps. Data structures help us optimize a lot with processing, because the better a data structure fits the data set and the problem you're going to solve, the more efficient your algorithms are going to work on that data. I mean, if you think about like a library, worst case scenario, the books are just put wherever. So if you want to find a specific book, that's going to take, O of infinity, possibly. You're going to have to go up and down each stack and each shelf looking for the books, right? The book that you want. If they're grouped by genre, let's say you want a book on the American Revolution, so you can, if they're grouped kind of by specific topics, then you can go to nonfiction, you can go to history, and you can go to American history, and now you have a much smaller set to look at. So you've taken your O of infinity problem to O of n squared. Still not ideal, but much better, just by changing the way everything, was organized and structured. And then if you take that one step further and you apply the Dewey Decimal System, right, then you have a specific number that corresponds to that book, which is broken up by, the initial 3 to 4 numbers, 3 to 4 more numbers after the decimal place, and then a couple letters. So you can go to the section that holds the first 4 numbers that you're looking for, go to the shelf that holds the next 3 or the stack, and then work that down and find the book you're looking for a lot more efficiently, because it's organized and stored in a sorted way. So it's much quicker to find things. And that's kind of how I want you to think about data structures. You got to find the data structure that's right for the problem that you're going to solve. So the first data structure we're going to look at is a stack, which is basically, it's exactly like it sounds. So if I have a countertop and I'm stacking plates on it, like I put a plate down on the countertop and now I have one plate, and then I put a plate on top of that, and a plate on top of that, and a plate on top of that. And let's just say hypothetically, like they're heavy, expensive plates, so I can't take one from anywhere but the top. So if I want a plate, I take off the top plate. So it's a last in, first out data structure. So in order to get the plates that are farther down in the stack, I have to take the plates off from the top on top of them. So there are really, when you're talking about stacks, there's a couple of fundamental operations. You should be able to push, which puts a stack on top of the plate. You should be able to pop, which takes the stack off the top of the plate. And you should be able to peek, which is just, you should be able to see what the element on top of the stack is. So we're going to implement, oops, what did I do? So we're going to implement those in Python. So the first thing I'm going to need is a class. We'll call it myStack so it doesn't conflict with any of the built-in data classes. And then let's define a constructor for myStack. So who could tell me, like, what kind of Python built-in data structure do you think we can modify to represent a stack?
A list.
Okay, so what do you think that I want to initialize that list to in my constructor for myStack?
I'd probably just do an empty one.
Yep, we'll just make it an empty list for now. And then if I want to push an element onto the list, how would I go about doing that?
Like append?
Yeah, append. So I want to do self.base.append an element. And if I want to take the last element, how would I go about doing that? So there are two cases we need to worry about here. Is the list empty or not empty? Because you can't take an element off an empty list. So how should we check if our list is empty?
Probably
Is-
the length is 0.
That's one way to do it. Will definitely work. Another way to do it is, so what's the empty list? What's the Boolean value of an empty list?
False.
It's false. So if it's not empty, it'll be true, right? So, and then we can just, how do I take the last element of a list? It's just pop, just like we're calling in the stack. So that'll take the last element else. And we'll just say, for starters, we'll just return none now. We also want a way to print or return a string representation of our list so we can print it. Or sorry, we need to do peek first. We'll come back to that. And then peek. When peek, we just want to look at the top element of our list. So it'll be similar to pop, right? If there's nothing there, we want to return none. So we'll say if self.base. So how do we look at the last element of a list?
Index -1.
Yeah, I think that should work. Self.base -1. Is that what you're saying?
Yes.
Okay. Else we want to return none. And then our string representation. So let's say we want to print out all the elements of the stack separated by commas. So how would we do that? Someone who has an answer before can help me. Tim, how would we start printing out all the elements of a list separated by commas?
Is it different than JavaScript?
It should be, the syntax should be similar. So what are you thinking? So
So
let's say,
would I be
I want-
returning the entire array, or am I returning just everything individually?
you're returning a string that represents the entire array or stack for the purposes of this.
Would it be join?
Yeah, we could use a join. How would we do that though? Because the element can be of any type. But I guess it's just a list. So what would be the syntax for a join? Like, what are you thinking?
I would probably do the output in the output string. Yeah, dot join.
That,
Yes, I think so.
okay. So let's go ahead and make a stack. So who can tell me, so what the difference between this and this is? Between, what happens if I leave the parentheses off?
It's not a function call.
What do you mean by that? Explain that a little more. You're going down the right path, but
Yeah, I mean, with the parentheses, you're calling that function
calling
Um,
the constructor, right? The init.
constructor.
Yeah, so this I will get a new instance of basically a my stack object if I have the parentheses. If I don't, I will get a pointer to the my stack class. I won't get an actual instance of it. So this will create a new, I should call it my stack, right? So let's add some elements to it. So if I'm going to print this, what should it look like? What should line 27 return or output to the console?
Would be the whole stack.
Yeah, it should just be jelly donut, comma, cinnamon sugar donut, comma, chocolate donut, comma. Let's give it a go. Let's see our code works. Really my code, I shouldn't say our code. Yep, so we did something. So here, why is it telling us? Because we have to return output string or just return this. Yep. And if we want to it tells us what the last element is. And then if we do my stack, Yep, and we could see that the chocolate donut was removed after we pop it. But does this make sense? Like, should it return none if we try to pop a list with nothing on it? Do you think that that's what happens in a stack in the standard library when we pop it? The answer is no. It's going to throw an exception. So if I want this to throw or to raise an exception, does anyone know how I do that? When I pop an empty, when I pop a list that has, or pop a stack that has no elements.
Can you do like a try except?
That's when I go to execute the code. So the first thing I need to do is create a custom exception. We'll just call it stack empty error, and we'll have it inherit from exception, and then it'll have nothing in it. And then we'll have this, instead of returning none, it'll raise a stack empty error, a new instance of it. Stack empty error, stack empty error. So now if I create a So what's going to happen if I run this program now?
It'll throw your error.
Yeah, so it'll raise an exception. So is this I mean, who was talking about try except blocks before? How would I wrap this in a try except block?
So the try will effectively try what you're trying, and then if it does not succeed in your accept, you can insert a specific type of error. And there's different kinds of errors. But the way you did it's a lot cooler.
What would you have done differently?
No, I like the way you did it a lot. It's a lot just so I like doing it as a class. It's just way better.
And this is the reason to prefer this is you still handle the exception, and your program can continue to execute if it does throw an exception, right? So something trying to pop an empty stack needs to know about that, because it's most likely expecting some kind of value. But in the event that it is empty, we can handle that case. A lot of times you'll just see them as print, but you can have whatever logic you want in here anyway, to have your code handle the case where you're popping from an empty stack or whatever exception is raised. See, and now we get the error. But this, I mean, this is just like any class. I can define a understring method to have it. And then I can just say stack empty error as E. So this is basically saying, if you catch a stack empty error, an instance of that class, so a stack empty error instance, save it under the variable E, and then I can just do print E, since I defined the string method for that class. So this should have the same result as the previous code that we had written. Yep. So you can't pop from an empty stack. what if I want to initialize a stack with an already existing list of elements? How would I do that? So I have a list of elements. So
Would
what
you
I
put
can
it into line 5 in like a parameter?
explain what you mean. So I want to pass it to my constructor. So this init function.
Well, no, I was just thinking when you're creating the class, like line 5, you do my stack and then have a parameter, and then you can pass in that argument,
Yeah, so
and
you
it would be fed into the class.
but I want to feed it into an instance of the class, like when I create a myStack object. So when I call this init method, which is what happens when I like line 37 here. So this myStack parentheses is calling this init method. So I want to pass something into it. So, but I still want to be able to create empty stacks. So what I'll do is I'll create a list of elements with a default value of the empty list. And then I'll say for elements in list of elements, I want to do self.push element. Right, so basically what this is saying is, and it's only going to go through this for loop if list of elements is not the empty list. So if I pass something in for list of elements, then I want to push that onto my stack by calling the built-in push function, which appends it onto the end of this, the end of the list. So I should be able to create a stack with some elements in it. Right, so this should create a stack with this at the bottom, this in the middle, and this on the top. So if I peek, it should show me M&M. Oh, I gotta make this a list. Very important. Yep, so that's just M&Ms. And then if I print the whole thing, it should just show all those in order. So that's kind of a stack. The key elements of the stack are push, pop, and peek. Personally, I always like, if I'm defining a class, to define the string method, because that can correspond to how the data is structured in the class, the way you return the string, and kind of help you understand what the data structure looks like internally. Okay, so next we're going to look at a queue. So a queue, very, very similar to a stack, except instead of being, excuse me, last in, first out, it is first in, first out. So it's exactly what it sounds like. Like if you're trying to go into a sporting event or a concert, you get in line behind the last person, and when you're the first person, it's your turn to go out. So you get at the end of the line, the first person is let out. Whereas a stack, you put the plate on top, so it's the last thing on, but then you take the last thing off also. So a queue is last in, first out, and a stack is last in, last out. So And it looks, the implementation looks very similar to a stack. So my init. We'll just say self.base equals that. And the key elements, the key functions for a queue are enqueue, which adds an element to the queue, and dequeue, which takes off the last element, or sorry, the first element. So this is just saying, whatever I have in my list of elements in my queue, just append this new element, which I make a list to the end of it. And then if I want to take the first element and return that. It's a similar case to stacks where I don't want to return anything from an empty queue. So we've got to check if self.base is true. So if self.base doesn't point to the empty list. And if that's the case, how do I get the first element?
Could you do it by index?
Index 0.
You could do it by index, and then list comprehension. But I think if we use the pop function, you can specify where to pop from, which would be a kind of more Pythonic way to do it. So I can just say, and I want the index at 0. So this will take the element off of my core storage mechanism and return whatever you took off to the user. If there's nothing there, I just want to return none. And then let's define our string method, and we'll just make it the same as we used for a stack. Okay. Looks good. So let's create a queue. Okay, so we're going to create a queue, my queue, and then we'll add Phillies, Braves, Dodgers to it, and then we'll print it, and then we're going to dequeue twice, and then print it again. So what should this last print statement print?
Dodgers.
Should print Dodgers, right? So last in, first out. So this will get put on first, second, third. So this is last, second to last, and then first. So it'll be Phillies, Braves, Dodgers, and then this DQ should return Phillies. And this DQ should return Braves. Let's take a look and see if I implemented it correctly. Oh, we got to return. We got to return statement. Yep. So first element to be DQ'd is Phillies, the second element is Braves, and then Dodgers is all that remains. And then we could do the same optimizations here where we create an empty queue error exception and raise that when you try to DQ from an empty queue. But the code will look very similar to this, except you should name your class something, your exception class something different. So that is queues. And then the last thing we're gonna look at are linked lists. So why do you think we look at linked lists? Like why would they be important? They seem like, you know, a node that points to another node that points to another node seems like a very inefficient way of representing data. And the answer to that is fundamentally, like linked lists are the basis. Like linked lists are, I don't want to say the base class, but the basis for implementing other data structures like stacks and queues. They'll be slightly more complicated than the implementation that we're going to work through, but linked lists are like a fundamental data type. You won't see them used a lot in outside of like libraries to define other data structures, but they're used as the basis for a lot of data structures. So I think y'all have done some challenges on linked lists, right?
I don't think so. I could be
No,
wrong.
not yet. Okay. So the way linked lists basically work is you have a node, and that node has two things. It has the value of the node and a reference to the next node or a pointer to the next node. So the linked list object itself just points to the first node. And then from that node, you can use the reference to the next node to get the next node, and so on and so forth until you get to the end. So insertion and deletion are fast. They're like, oh, one, just like they are for stacks and queues, but that's why they're used. Linked lists are used to implement stacks and queues. So the first thing we need to define is the node that's fundamental to a linked list. So, and it's pretty straightforward. So we want to self.value equals value, and self.next, which is a pointer or a reference to our next node, we'll just say by default it's none. So this is the value that's stored in the node, and this is the reference to the next node in the list. And then we can use that to implement a linked list class. And the first node in the list is traditionally called head. So, and to start, it'll be none. And then the fundamental operations on a linked list are insert and search. So insert for our implementation is going to add an element at the head, and all the other elements are going to shift one to the right. And then search is going to look through the linked list, and if it finds the value, return true, and if it doesn't, return false. So the first thing we need to implement is insert. And we need the element. We'll call it value, so I guess that's what we used up above. So how are we going to do this? You don't have to tell me the code, just someone tell me the process here. So we need to do what to insert a new node in the linked list?
You'd have to set that next value to like a new node with that value that you have on insert.
Okay, yeah, so new, you're saying create a new node with the value, right?
Right.
Okay, what next?
After you create the node, the new value, you'd have to grab like the head node and update its next value to
Okay.
the node that you just created.
Yeah, I think first we need to preserve
Oh yeah, yeah.
a reference to the old head, right? But yeah, so
Mm.
then we'll just say self.head. So this head of the data structure, we want it to equal our new node. And then for our new, sorry. So, and then self.head.next equals our old node. So what we've done is we put a node at the beginning of the list and attached all the other nodes to that node. And now we need to define a search function. So how are we going to do that? We basically have to, at the simplest form, walk through every element of the node until we find the value or get to the end of the linked list, in which case we want to return false. So we'll just do that iteratively. We'll say our current node equals self.head. And then while current node does not equal none, because at the end of the list, the current node will be none, right? So, and then if current node dot value equals value, turn true. Else, we want to say current, we want to go to the next node. So current node equals current node dot next. So basically, we're looking at, starting with the first node, we look at the value. We compare the value here. If it equals the value we're looking for, then we return true. If not, we grab the next node in the list. That's what this does. It uses the reference to the next node to update our current node. And then we go back here and we compare that value to the value we're looking for, turn true, go to the current node. And when it gets to the last node, current node dot next will equal none. So now current node will be none because there's nothing there for it to point to. And it'll return, and then we need to return false. And then let's just use our same string. Who knows with this? So I just used the built-in template. This arrow string is at the end of the function definition that auto-populated.
Function annotation.
What is this telling me? What's this string?
And you return a string.
Yeah, so this is a type hint for the return value of the function. So this is saying, hey, this function is supposed to return a string. But don't need that, so we will just make our linked list. So we need to traverse our linked list just like we were doing search, and basically do this to print every element. let's just put space on the end. Okay, so what we're doing here is very similar to our search function. Basically, we're stepping through our linked list and adding each value to an output string, and then we need to return the output string. So if there's no values in the linked list, it's just going to return, like if this is none, like if we haven't added anything to it, then it's just going to return the empty list. Okay, so let's define a linked list. Let's see if this works. So we should get Lions space Steelers when we try to print our first linked list. Not to initialize current variables. Yep, and that's what we get. Sorry, Steelers Lions, because it inserts it at the front. And then if we want to search, let's just say our search term equals Texans. Like, I don't know why you would name a team in Houston the Texans. Is Texans is number equals first linked list dot search switch. Now we'll do a prints. Grammar is killing me here. That seems like it makes sense. So it'll say it's true or false that the whatever the search terms is a member of the list. So this should return false if we've implemented this correctly. Yep, it's false that Texans is a member of the list, but it's true, should be true that Lions is a member of the list. It's true that the Lions, grammar's killing me. Okay, so that is linked lists. They're a foundational data structure, I'll say, in that they're used to implement a lot of other data structures because of their efficiency at insertion and deletion, but you won't end up using them a lot in practical code. You'll use data structures that are derived from them, like stacks and queues and those kind of things. So what questions do you have about stacks and queues and linked lists?
Could you go back to the end of your code? I'm sorry, I'm missing a few lines. So I just want to make sure that I got it right.
Yeah, absolutely. You talking at the end of the linked list class?
Yes, sir. That's it. My linked list object is not callable.
What question did you have about it?
I'm just getting an error that says my linked list object is not callable. Well, line 118, which is lions. So
We can take a look at it after the break if you would like.
yeah.
Okay, what other questions do you all have?
So after you created your second class, I think it was the queues, right? Well, it wasn't your second class. The second part of this lesson, when you talked about queues, you said on your try catch that you don't want to do the same exception class for that. And why is that if it's going to throw the same error?
Because I want it to be specific, the naming convention, just for readability. Like I could make this just an empty error and use it for both, or I could make it a stack empty error and a queue empty error. It's the same error, but
just to be more specific.
say that you don't have something that's going to catch the error, then probably all you're going to get is the name of the class. So I kind of want more information in the name of the class when the error is thrown, in the event that, you know, it ends up raising it somewhere that I don't expect it. So when it prints out to the terminal or the console or whatever, I'll have more information about what happened. Does that answer your question?
Yeah, that makes sense. Yeah.
Okay. Let's go ahead and take a 10-minute break. We'll come back at 7:10 and we will take a look at the challenges for tonight. So I'll see you all back at 7:10 Central.
Sean, would you mind pushing your file to get for us?
I will push it at the end of the session today because your challenges are basically doing what I just did. But I'll put it up towards the end, like closer to 9.
Yeah, thank you.
Yep. Okay, let's go ahead and bring it back in and take a look at the challenges for this evening. Okay, so there's two challenges. They're essentially the same, except the second one has some additional stretch goals. So we'll look at data structures 1 first. So your challenge is to implement basically the 3 implementations that I went through during the lecture. So a stack, using the methods that are in the file. So you have a linked list file, a queue file, and a stack file. And for stack, you've got to do a push pop peak size and is empty method. And for linked list, you've got to do insert, search, remove, size, and is empty. So I think the intent here with remove is you want to remove a specific node, not just the head or the tail. So if you have a linked list that is like 2, 4, 6, you want to remove node 4 and then size. And queue. So you have enqueue, dequeue, peak, size, and is empty. So basically what I did in the lecture with a couple of additional methods. And then the second one is very similar, except there's some additional binary search tree and a hash table. So binary search tree, you're going to have a node like a linked list with a value, but then it's going to have references to 2 other nodes like a tree. So let me see if I can find a good picture of one. Yeah, so here's a good picture. So this is my first node, and then so the value is 8, and it's got pointers to 3 and 10. So all nodes, so you have a left pointer and a right pointer, and then all nodes in the left tree are smaller than the parent. So this is a parent, children to these parents, children to these parents. So basically everything in this tree, the 1, 3, 6, 4, 7 is all less than 8. And then 3, so everything in the left tree for 3 is less than 3. So 1 is less than 3. 6 is greater than 3, but everything in the left tree here, you have 4 is less than 6, and 7 is greater than 6. And then you want to know, how would we traverse a tree? Basically, you want to know how you're going to walk through every node in the tree. So when you're looking at a tree, this is level 0, where the 8 is. Level 1 is the 3 and the 10. Level 2 is the 1, 6, 14. And then level 4 is 4, 7, and 13. So how do we visit every node in the tree? You could do it at breadth first. So start level 0, go through all the nodes at level 1, all the nodes at level 2. Depth first. So depth first is basically you're going to go all the way down a branch until you get to the end, and then go all the way down another branch until you get to the end, next branch until you've traversed all the branches. Oh, I guess there was an example. Nope, there's no. I'll have to fix that. And then hash tables. So hashing, used a lot in cryptography, and it's basically you have some function which is sufficiently random to turn a value into a numeric value. So some function that takes in an input and produces an output, but you cannot go back from the output to the input. So basically it's a one-way algorithm. So if I have, let's say, a value of like Houston, and that turns into 1, 2, 3, 4, 5, 6, 7, I can't go back from 1, 2, 3, 4, 5, 6, 7 to Houston. But if I put Houston in again, I should get 1, 2, 3, 4, 5, 6, 7 again from the function. Like the function should always produce the same result. So the challenge is to construct a Q stack, binary search tree, and hash table in the functions in the repo. So the core of the challenge is to do Q stack and linked list, and then the stretch goals, if you get to them, are to do a hash table and a binary search tree. And then here's some more discussions of data structures and how they work with, you know, the way that they're organized in memory. This will be useful to read if you're going through hash tables, I think, in particular. What questions do you all have about the challenges? Okay. So I will turn you loose to work on them. If you have any questions or issues while you're working through them, excuse me, feel free to post in the chat or just ask in the general room here. And so that's it. Good luck on your challenges. We'll try and regather in the main Zoom room for end of day at about 9:10. And I think someone had a question about their implementation. Was that you, Chad, earlier?
No, it wasn't me.
Who was asking about the linked list?
I think it was
That-
Matthew.
Yeah, that was
Matthew.
me. I
Okay.
was following your code and I was running into some errors, but if you want to, we can just go through it after if you like, or it doesn't.
Yeah, whenever you want to go through it. If you want to go into a breakout room, I'm happy to help now, or I can help later if you want to look at it a bit more.
Okay.
Just let me know. Okay.
Awesome. Yes.
Yeah, Hyder and I will be here if you need anything. So post in the Slack chat.